In this presentation, I will go over a thermomechanical workflow for a high-density advanced package. So here, SimCenter FlowTherm is used to solve for the temperatures, and then that data is brought into SimCenter 3D for structural analysis where warpage and creep is analyzed. Okay, so jumping into the workflow, we have a fan-out wafer level package that is designed in Expedition Package Designer, where two dies are mounted on an organic substrate. And then this model is brought into SimCenter FlowTherm through EDA Bridge, where it is thermally analyzed. The temperature profile of the package is then imported into SimCenter 3D, where structural analysis is performed. Here we have a showing the SimCenter FlowTherm geometry preparation and boundary conditions. Starting in SimCenter FlowTherm, EDA Bridge is first opened. With a range of EDA data formats supported, an ODB++ representation of the fan-out wafer level package exported from Expedition Package Designer is selected. U1 and U2 components represent two dies. They are selected and a silicon material is applied to both. The percentage coverage of copper on each of the redistribution layers is extracted from ODB++. Instead of the copper being assumed to be equally redistributed over that layer, a refined thermal representation of its distribution can be controlled by the slider bar. In this case, a resolution sufficient enough to resolve all the pads that will connect to the C4 bumps. The same approach is taken for the bottom layer with a resolution selected to resolve all the micro bumps connection points. Once the ODB++ data has been thermally prepared, the thermal model of the package is then transferred to FlowTherm. A more refined thermal representation is achieved by creating a metallization layer on the flip side of the chip with the appropriate materials assigned. The power dissipation is defined in the active layer of the die. The active layer is placed between the metallization layer and the rest of the silicon. Now, skipping a few geometry preparation steps for the sake of time, here's the final package. The organic substrate was brought in and processed the same way as the fan-out wafer level package in EDA Bridge. Here we see the individual layers, each with different conductivity values that were derived from EDA Bridge on the fan-out wafer level package. If we hide the metallization in active layer, we can see the bumps as well. Now let's take a look at the active layer power source. Attached is a 1 second on, 1 second off pulsing power. The total time for this thermal transient analysis is set to 10 seconds. Here we look at the transient properties. 10 time patches are created with an increasing power distribution type for every 1 second. This ensures we capture the power transition areas with increased time step resolution. Also, I wanted to mention new in SimCenter FlowTherm 2210 is the ability to represent sub-microsecond time variance for power cycling and time steps. Now we solve the SimCenter FlowTherm model, and here we're looking at the surface temperature plot over a 10-second period. Now we can start exporting data from SimCenter FlowTherm that is needed in SimCenter 3D to perform a structural analysis. First, we export the field data, which consists of the temperature results of the package. When we select that export option, we have the ability to filter which time steps we want to export the temperature results from. In our case, we export from 8 to 10 seconds, so we use the filter option starting time from and set it to 8 seconds. Next, we export the CAD geometry by going to the Export Project option. Next, what is SimCenter 3D? SimCenter 3D is the most comprehensive, fully integrated CAE solution. It has the ability to both import geometry or create geometry as it's based on the NX CAD platform. So as you see on the wheel on the right, it has many different CAE modules. So for example, for structurals, it can handle linear and nonlinear loading and set up all the appropriate parameters such as meshing and materials and properties for that. It can solve for things such as creep and fatigue of a model. For dynamics, for example, you can do structural vibrations and structural behaviors. For acoustics, so for example, In an electronic box, you can simulate the acoustics of a fan. Here's a slide on the overview on how to set up the SimCenter 3D model using the SimCenter Flowtherm data. First, we open up the CAD file that was exported from SimCenter Flowtherm. Then we assign the proper materials to the model. Next, we create a structural mesh and glue simulation objects across the various layers. Then we apply the thermomechanical boundary conditions, including the FLD file containing the temperature profile of the package from SimCenter Flowtherm. And finally, we set up a nonlinear solution requesting warpage, creep, and other metrics of interest. After solving this SimCenter 3D model, we take a look at the results. There's a variety of ways to look at results, from stresses and strains and so on. Here we are looking at the von Mises stress, which is a value used to determine if a given material will yield or fracture. And as expected, as we can see on the right, there are higher levels of stress at the corners of the package solder balls. Here we're looking at the warpage. The scale here of the deformation was magnified for better visualization. And finally, our nonlinear analysis of creep strain. This shows our solid material that could permanently deform under the influence of stress. And that concludes my presentation.